Hi guys, this is topic 8.9, the Henderson-Hasselback equation, and that's what we're going to cover today. So the objective is to be able to identify the pH of a buffer solution based on the identity and concentrations of the conjugate acid-base pair used to create the buffer. So this is just an extension of 8.8 buffers, and you actually will see a very similar problem that continues onto this lecture. So, like I said, we're revisiting the buffer. We formed an 8.8. It contained 2.00 moles of acetic acid and 2.00 moles of sodium acetate dissolved into 1 liter of water. Makes it easy for our molarities. This was a buffered solution since both the weak acid and its conjugate base are both present. We can look up the pKa for acetic acid and use it to calculate the pH of the buffer system using the Henderson-Hasselback equation. So you see that to get the pKa, or the pH, I'm sorry, so we are using the equation pH equals pKa plus the log of the conjugate base over the acid, the concentrations, the molarities. So if it's 4.76, we plug it in to find the pH, because it's 1 and 1, 1 over 1, I'm sorry, the pH will equal the pKa for this particular buffer system. So the pH and the pKa, like I said, are the same because the concentrations of the conjugate acid and base are equal. The log of 1 is 0, so it drops out. The pH of a buffer is dependent on the pKa of the buffer that's given, or you can get it, and the ratio of the concentrations of the acid-base pair. So like before, if we add 0.0100 moles of NaOH, it will react to form the conjugate base as shown. It's a strong base, NaOH, and it's the limiting reagent, so we assume it's going to be all used up. So that means that the concentration is going to be the number of moles will be all gone, as shown here with the 0. Notice how when we get our equilibrium, if you will, concentrations, we plug it in, the pH still stays the same as 4.76. Same idea applies to adding an acid to the buffered system. So we add 0.0100 moles of HCl. It reacts with the acetate to form acetic acid. Again, the HCl is strong and it's a limiting reactant, so it's going to be used all up. So again, just using the same chart as before, the pH is still the same, 4.76 after all is said and done. You're going to plug in the conjugate here, and then you're going to plug in the concentration of the acid according to the reaction. So in the end, you end up with a pH that's pretty much the same as before. So that's why they were able to resist changes in pH. Calculate the buffer of a pH solution for a weak acid, just a random one, HA, if the concentration is 0.137 molar and the concentration of the conjugate base, I'm sorry, is 0.972 molar. The Ka for this is 1.5 times 10 to the negative 5. So the fact that they gave us the Ka, and remember this is the equation though, pH equals pKa plus the log of the conjugate base over the acid. So that means I got to figure out what the pKa is first if they gave me the Ka, if that makes sense. So to get the pKa, it is negative log of the Ka, 3 sig figs, that will give me a pH, a pKa, I apologize, of 4.821. So I'm going to plug that into my equation to solve for the pH. So it's already a buffer solution with the following concentrations, So that makes it easier on us. We don't have to worry about figuring out the concentrations, what it is at the end type of stuff. So then it's going to be 4.821 plus the log of the 0.972 concentration over the 0.137 molar concentration. This equals, you just do the calculation, plug in your calculator, you will end up with 5.672 for my pH for this. Just follow the equation. It's not that bad of a type of math problem. Calculate the Ka. So we want to figure out what the Ka is based on the following solution. We have some unknown acid, HA, and the pH of it is 4.219. The buffer contains 2.43 moles of HA and the 1.75 moles of NaA, and it's dissolved in 1.92 liters of solution. So here, for these past couple of problems that we're going over now, there is nothing that's, I guess, added new, if that makes sense. There's no like an additional OH or an additional H, all that type of stuff. It will tell you if they tell you that if some acid or base is added, that's when you have to do the ice chart. But for now, for these stuff, you don't really need to do that. So calculate the Ka that we are trying to find. So remember, pH equals pKa plus the log of the conjugate base over the acid. So how do you find this? So essentially, I say that a lot, I know. You have your pH. You have your acid here. You have the base right here. You can get the conjugate base from there. The moles of that. And they tell us it's in a 1.92 liter solution. So we can figure out our molarities for this particular thing. So to solve for pKa, it's going to be the pH minus the log of the conjugate base over the concentration of the acid, and that will equal my pKa. So 4.21, we're going to break this out. So 4.219 minus the log of some fraction, and that will equal my pKa. So to find this, we got to find our concentration of both the acid and the conjugate base. So to find this one, the one on top, it's the moles of this. So luckily, we see that it's in a 1-to-1 ratio. So it's going to be 1.75 moles of just the conjugate base divided by 1.92 liters. It's supposed to be a 9. And that will equal 0.911 molar. Find the concentration of the acid. So it's the moles of 2.43 moles of HA divided by 1.92 liters. 1.27 molar. I'm going to plug all that in here. 0.911 divided by 1.27. So essentially, I'm just going to do a calculation. I'll end up with my pKa equaling 4.363. However, I'm not looking for that. I'm looking for the Ka. So how do you find the Ka? Thinking about our pH chart and all that. So Ka equals 10 to the negative 4.363, and that will equal 4.34 times 10 to the negative 5. So remember, this is 3 sig figs because that's 3 sig figs right there. Just a reminder. All right, so if you have any questions, please let me know. Thanks, guys.